This lesson deals with the 555 timer and one application called a monostable. You can find these notes in the ECE402 ebook in Chapter 7 starting on page 1. Fairchild Semiconductor introduced the op-amp in the late 1960s, and it took off as a basic building block where you could make a lot of different frequency domain circuits. About 4 years later, Signetics introduced a circuit that could be used to make a lot of different time domain circuits, timing circuits, controlling circuits, things like that. Over the years, the 741 op-amp became the highest selling analog IC. The second highest seller is the 555 timer. This is what's called a functional block diagram. It's a simplified equivalent circuit of what's inside the IC. We got some resistors here. We've got a transistor, another transistor, comparators, a flip-flop, and an inverter. I have a voltage V sub CC here, and the current going into the comparators is very, very small. So pretty much all the current goes down this path. And so having 3 equal resistors, I would have 1/3 of the power supply here, and I would have 2/3 of the power supply here. Those become the reference voltages for the comparators that we'll talk about in a little bit. The flip-flop that's here is like a standard flip-flop, but there's a couple of special things about it. Let's take a look at the truth table for this. When the R pin, which is the reset pin, and the set pin are both low, the state of the output out here, which we'll call Q, has no change. And initially it's just low. The complement of it is just the opposite. It would be initially high, and it would also have no change if this was the case. This will be important for how we're going to use this particular flip-flop. Now, if the reset is low and the set is high, the output goes high and the complement goes low. If the reset is high and the set is low, then the output goes low and the complement goes high. Here's where there's a state of the RS flip-flop that normally is undefined, but because this is a specific set of transistor, it does something, and it does impact some applications. So if both the R and S are high, then Q is high and its complement is low. This is something that'll problem to take a look at using that. Now, how about the discharge transistor that's in this picture? Let's take a look at what's driving it. So the output, before it goes through the inverter, is fed back to this discharge transistor. And so when this signal is low, it really means it's a low voltage, this transistor would be cut off. It wouldn't be doing anything. And of course, when this is high, we'd have a larger voltage here, and this could go active or saturated, but they've actually picked it so that this saturates. Let's next take a look at the PNP reset transistor. Let me flip back actually to the last page. Here's a transistor here. This is labeled as 2 V sub D. That just means it's 2 diode drops. This is sitting at about 1.4 volts. So if the R sub S pin is lifted up to the power supply, say VCC, then the voltage from the emitter to the base would be a negative number, and the transistor would be cut off. If this pin is pulled low, then I'd have 2 V sub D across here, and I would definitely have a lot of current coming out of the base, so that would saturate the transistor. Now when it's cut off, it doesn't do anything, and Q barge is just fed into this transistor, but when you saturate this, it forces the voltage here to be 2 V sub D, and that actually makes this transistor also saturate. Let's next take a look at the threshold comparator. Again, let's go back to that previous page. That's the comparator here. This again is sitting at 2/3 of VCC. So when this voltage is less than 2/3 VCC, the voltage from here to here would be a negative number. In other words, this minus something that's bigger than that would give me a negative, and that would give me a logical 0 on the reset line. Now, if the opposite's true, if this is bigger than 2/3 VCC, then this is positive. This goes high, and it gives me a logical 1 on the reset line. Take a look at the trigger comparator. Of course, the opposite's true here. This is sitting at 1/3 VCC. So when the trigger is greater than 1/3 VCC, the voltage across here would be this minus something that's bigger. So that would give me a negative number, which would make this go low, give me this a logical 0. The opposite case, if this was less than 1/3 VCC, then the voltage from here to here would be a positive number. This would go high and give me a logical 1. And lastly, this control voltage pin is sitting at 2/3 VCC, but you could put a Zener diode here and force this to be whatever voltage you want it to be, but it had to be less than VCC. But whatever voltage you put here, you still have 2 equal resistors with the same current going through them, So you get half the voltage. So whatever this is set to, this will become 1/2 the value. Normally we won't put anything here. Occasionally put a capacitor here to act as a filter so that no noise gets in here, because this upsets the reference for these comparators. And all this is stated on this page. Let's take a look at what's called the monostable mode of the 555 timer. The circuit was invented so that we could make pulses and a lot of other things very quickly by just adding some simple components like we do for an op-amp. Let me give you a trigger signal here, which is going to be coming in on this trigger line. And it's going to start out at some voltage that's bigger than 1/3 VCC, and it'll drop down below 1/3 VCC for some amount of time, then come back up again. What I want to show are these resulting waveforms and why they're true and what their values are. Let's start at time t equals 0. Assume that this capacitor is not charged, and then see what happens when we apply a voltage here that's, I don't know, say VCC in size. Okay, so I got a large voltage here. With this voltage here being greater than 1/3 VCC, we can go back and take a look at our drawing back on page 1 and see what happens. So if the trigger is greater than 1/3 VCC, that means that if I take 1/3 VCC minus a number that's bigger, we're going to get a negative number, and that's going to make this go low. That gives me a logical 0 here. Go back to our circuit again. Now the voltage across here is initially 0, and it can't jump instantaneously, so at t equals 0 plus, the voltage here is still 0. So let's take a look at what happens when you put 0 volts on the threshold line. So I put 0 volts here. I've got this voltage minus 2/3 VCC, and that's going to be a negative number, and so I'll get a logical 0 over here. So what that means, if we go back to our table, back on page 1, is that when both of these are 0, there's no change in the output. But if this is occurring initially, this will be low. In some sense, it would be just thinking of it when the chip wasn't on, the output was low. And turning the power on, if this is exactly what happens in power up, this would still stay low. So let's go back and look at this explanation here. So we're just looking at really this instant right over here. So the output's low. I've got two things labeled here, the output high and the output low. This is approximately the power supply, and this is approximately 0. We'll get more specific numbers from the data sheet a little bit later in the course. So nothing happens until that trigger pulse goes low, and we'll see what happens next. I forgot to mention one more thing. When the output is low, the complement is high, and the complement's what's driving the discharge transistor, and that causes this to saturate. So what we've got is a short across this capacitor. So the voltage across the capacitor starts out at 0, but it doesn't change because we're basically putting a saturated transistor in parallel with it. You can just think in a very simple sense, just a short circuit. Okay, so suppose now we get up to time t1, and just at t1 plus, what happens with the trigger? Well, it goes from something bigger than 1/3 VCC to something less than it. Suppose that this is just say VCC, and we just drop to 0. Okay, let's see what happens in our block diagram here. Let's erase these previous calculations that we did. Okay, so now the trigger has dropped to 0 volts, and so the voltage from here to here is going to be 1/3 VCC minus 0, so that's a positive number. That's going to make this go to logical 1. It goes high. Now the capacitor voltage can't change instantaneously, so the voltage here is still 0 volts, and the voltage here is 2/3 VCC, and so we get a negative number, and so this is going to go low. This is logical 0. Okay, this is going to cause the output to go high and the complement to go low. With the complement going low, this transistor is cut off. Okay, now what's going to happen? Well, with this transistor cut off, there's nothing in parallel with the capacitor, and now this RC circuit can begin to charge. So it'll charge towards the power supply. Let's see if we can figure out the equations for it, and this is on the bottom of the page. This charge transistor is cut off, so there's no current going in here. Our comparators don't draw any current, so we basically just have an RC charging circuit. So the voltage across the capacitor is some A plus B times e to the minus quantity t minus t1 over tau, where t1 was the instant where our pulse dropped down to 0 volts. The value of tau is R1 times C1. All right, what's the voltage across the capacitor at time t equals t1 plus? Well, it's the same as t1 minus, and that was equal to 0 volts. So it's going to be equal to A plus e to the 0, which is 1, which is A plus B. Now, if you wait long enough, the capacitor will become an open circuit, and the voltage across here will just be equal to the power supply minus the drop across the resistor, but we're not drawing any current, so this is going to be equal to the power supply. So it's the value of A. So now I go back and solve for the voltage across the capacitor. So we know that A is equal to VCC, and we have A plus B is equal to 0, so B must be the negative of A. Just pull that out in front. So I've got 1 minus the quantity e to the minus T1 over R1C1 for the expression of the charging capacitor. So for T greater than T1, the voltage across the capacitor is also the voltage of the threshold pin, and this is our charging capacitor equation. Suppose that the RC product is big enough such that this capacitor, as it'll start to charge the VCC, doesn't make it to 2/3 VCC by the time we come back up again. And I'll call some time T2. So what does that mean? Let's go back and look at our diagram. Okay, the threshold pin is the capacitor voltage, and that hasn't reached 2/3 VCC yet, so the voltage across here again is still negative, so we get a 0. But now the trigger has returned back to a number that's greater than 1/3 VCC. So now the difference here of 1/3 VCC, say minus a number that's bigger, would be negative, and that would now make this go low. And so we have now R and S both 0, and what that means at the output is that nothing changes. The output was high, and the complement is low, so this transistor is still cut off. And so nothing happens. So we stay high past T2, and now nothing's going to happen until we reach 2/3 VCC. So let's take a look at that case next. Now what happens as we cross T3? So let's say T3 plus. The voltage across the capacitor, which is also the voltage of the threshold pin, has now just slightly exceeded 2/3 VCC. Let's go ahead and look at our block diagram. So now we've got the trigger still back up greater than 1/3 VCC, so this is still 0. But now the threshold pin has just crossed over the value that's hooked up here. In other words, this is a little bit bigger than 2/3 VCC. That's going to cause this to change state. The difference will be positive, and this will go to logical 1. So this means that we're going to reset the output. This is going to go low, and now this is going to go high, and that's going to saturate the transistor, which is pretty much like putting a short circuit across the capacitor. So let's see what's going to happen. So the capacitor is going to start to discharge very quickly. Well, initially we're a little bit above 2/3 VCC, and now we're a little bit below it. So what's going to happen to the output? And the output went low because we crossed 2/3 VCC, but what happens now when we just drop a little bit below 2/3 VCC? Well, let's go back to that block diagram now. The trigger is still high, so the difference is negative, so that's still 0, but now this is less than 2/3 VCC, and that means that the difference is negative, and this goes to logical 0. And that means no change in the output. So the output then went low and stays low. And so what we've got now is that we have call it trigger pulse, that is a certain width. It can actually be kind of sloppy, and it creates a very precise pulse out. See if we can solve for the pulse width. Let me mention one more thing here. When we went through this last state, we have our output going 0, our trigger is greater than 1/3 VCC, and our reset and set lines are set equal to 0. And so we're back to where we started from at the beginning of the monostable. So we're basically creating again a pulse based on a little, call it triggering event. But again, this can be really almost any width, as long as that when this goes back up, we haven't reached 2/3 VCC. You can figure out how long it takes to go from 0 volts to 2/3 VCC. Well, we have the equation for that, so we can just solve for it in terms of the R's and C's. Okay, so when T is equal to T3, the capacitor voltage, which is also the threshold pin, reaches 2/3 VCC. We're going to take our equation and just plug in T equals T3. And now we're going to solve for the difference between T3 and T1. Bring this on this side of the equation, so I have VCC times 1 minus 2/3 VCC, so that's 1/3 VCC, and put this on the other side of the equation, which has got a VCC in front of it, and then this exponential term. You notice here that the value of the power supply drops out. So that's good. If you have a battery-operated system and the batteries change a little bit over time, it won't affect the width of the pulse. I'm going to take the reciprocal of both sides of the equation to get rid of this minus sign. So I get a plus, and then the 1/3 becomes 3. Take the natural log of both sides of the equation. What we get then is just the argument here. and cross multiply by R1C1. So T3 minus T1 is equal to R1C1 times the natural log of 3. Natural log of 3 is 1.0986. Mostly we'll just approximate that as 1.1 R1C1. And so this is the 555 timer and one application called a monostable.